Oh my goodness, electric potential difference. I hope you guys are ready for this. So this is also known as electric potential or voltage. You've heard that word before. You probably don't know what it means, but you've heard it. So that's exciting. So that's now you're going to figure out what the heck voltage means. What is it? It just means it's how much potential energy a charge has per unit of its charge in an electric field. Okay, that's it. So that's what voltage is. It's just how much potential energy does that charge have to move towards or away from a different charge for every unit of charge that it has. Okay, so if that's the definition, that's how we're going to calculate it as well. Potential energy divided by the charge, where V is voltage, or delta V is the change in voltage. So that's measured in volts, which is technically joules per coulomb, but we give it a special thing called volts. EP is your electric potential energy. So that's a type of potential energy we've never really looked at. So we're going to go into what does that mean. So remember, potential energy is stored energy. So if I put a negative charge next to a positive charge, they now have potential energy because they're going to attract each other. So that is in joules because it's energy. We can also measure that in something called electron volts, and that is something that they use for this more often because it's a much smaller unit and is easier to use. And so that's 1.6 times 10 to the 19 joules. Okay, and why is it that? Well, an electron volt, okay, an electron volt is the amount of energy gained by one electron moving through 1 volt. Okay, so that's what an electron volt is. It's the amount of energy gained by 1 electron moving through 1 volt. And then when you look at that, it makes a lot of sense because that's potential energy. And if we have 1 volt and 1 electron, that's 1.6 times 10 to the negative 19 coulombs. So then it starts to make a lot more sense why an electron volt is 1.6 times 10 to the negative 19 joules. Okay, so that's what an electron volt is. But just all you really need to know, it's another way of measuring energy. And so if you ever need to convert between joules and electron volts, there's your conversion, which is also on your data sheet under constants. And then Q, of course, is charge in coulombs. So let's really talk about this potential energy. So you're not really able to measure just the potential energy of a charge at any point. You need like a reference point to measure it with. Okay? So in order to measure potential difference, you have to have 2 points. Choose some reference such that the voltage at 1 point would equal 0, and then I want to know the change in voltage. So again, if at the example of having a positive and a negative charge away from each other, when they have 0 volts between each other is when they're right together, okay? And so I move this one away, and all of a sudden, my change in voltage is my change in potential energy, okay? Because here is when it has potential energy. Here, there's no more potential energy left because the 2 charges that are being attracted to each other are together. So let's draw a few diagrams just to compare it, because I want to compare it with something that you have a lot of context for, you've been dealing with since grade 10, and that is gravitational potential energy. Because I think as far as gravitational potential energy goes, we all understand that. When does something have gravitational potential energy? When it's held above the ground, right? So at this point, when it's at its maximum height, when it falls above the ground, that is, of course, when it has the greatest gravitational potential energy. Unless I lift it up higher, and that has even greater. But in this context, say that's the highest you can hold it up, that's its greatest potential energy that it will reach. And this is a case where we have no velocity, so that's velocity, not voltage. And so therefore, kinetic energy is 0, okay? But as it falls down, what happens to your gravitational potential energy? It goes down as kinetic energy goes up, right? So that's something we know about potential energy. As the thing that's being attracted to the other thing, here we have the ball being attracted to the earth. As the ball gets closer to the earth, the less potential energy it has, right? Because that stored energy is actually being converted into kinetic energy, okay? And so then, of course, once the ball's here at the bottom and your height's at 0, then your potential energy is at 0 because all that potential energy has been converted into what? Kinetic energy. So that's when the kinetic energy is at its maximum and the velocity is also at its maximum, okay? And so I want to compare this to, say, electric potential energy. So I'm going to have a set of parallel plates, which I know we haven't talked about much yet, but that's one where we have one plate that's uniformly charged as a positive and then one plate that's uniformly charged as a negative. So then this just creates a nice uniform electric field that I put any small charge in there, and it's always going to want to go towards one or the other. So say I put a positive charge in this lovely electric field where there's a point at which that I put a positive charge, it will have maximum potential energy, the maximum amount of potential to move. Is it near the negative plate? No, because that's where it's going to want to go anyways. So if I put the positive charge over here and by the negative plate, no, not a lot of potential energy anymore because that's where it wants to move anyways. So how do I get the greatest amount of potential energy here is when I put it at the positive plate. It's the farthest away it can get from the negative plate, and that's when it has the greatest amount of potential energy because, of course, we know what's it going to want to do. It's going to want to move towards the negative plate, okay? So this is when your potential energy is at its maximum, which here means your voltage is at its maximum, voltage being potential energy per unit charge, okay? So they are very closely related. And what's this positive charge going to do as it's moving towards the negative plate? Well, all that potential energy is going to convert itself to kinetic energy again. And actually, in these situations, since we're dealing with such much smaller things, then actually it's more likely that all potential energy will be converted to kinetic and very little will be lost to something like heat. So this is when, of course, our velocity, I'll put a little vector on top of it so you know it's not voltage, is at its maximum, okay? So remember, voltage is capital V, velocity or speed is lowercase v, but always just put that vector on top of v just so we know, okay? There's another way we can set this up. What if I had a negative charge? What would I do there? Well, we could do the similar setup with the parallel plates, but I'm going to put the negative plate on this side now, okay? And the positive plate over here, and we'll have the same situation happening, or same looking one if I put a negative charge here. Where would it have the greatest potential energy? Closest to the negative plate, because again, it's being repelled by that negative plate, it's being attracted to the positive plate. So this is when it has its maximum potential energy, because that's the place that you put it to have the absolute maximum potential for it to move, right? So therefore, that's when our voltage is at its maximum. And so, of course, halfway through, we'd have half our potential energy and half our voltage. And of course, once we fully get over to this side, that's when you have your maximum kinetic energy. All the potential has been converted to kinetic, and all your voltage has been converted into velocity. Okay? And so that's what potential energy looks like for charged particles. Okay? So if we're looking at energy conservation, we know gravitational potential energy is gained only if there's work done in the object to move it up against the gravitational field of the Earth. Same thing with electric potential energy. You only can gain electric potential energy if work is done on the charge, again, against that electric field. Okay? And specifically, it has to be work done against in a certain direction. Because if I move something, if I like hold something about a ball above the ground and I move it horizontally, doesn't matter. Potential energy is not going to change. But if I move it vertically up, oh, that's definitely going to change its gravitational potential energy. So similar with those parallel plates, you really only do work if you change the charge parallel to the field or perpendicular to the plate. So again, going back here, if I move this positive charge up or down, I'm not changing its potential energy whatsoever, because that potential energy is still, it's still the same distance from the negative plate, which is, again, the one that's attracting it, and the positive plate's repelling it. I'm only going to do work if I move it against where it wants to go. That's when I'm going to do work, okay? And so it's very similar with our gravitational potential and electric potential. The only way that you can gain more potential energy is by working against the field that you're in, okay? So then if the object is released, then all that potential energy goes into kinetic energy for both of them, right? As we drop the ball, the gravitational potential energy decreases and the kinetic energy increases at the same rate. With the charged object, you release it, and then the kinetic energy will increase at the same rate that the potential energy will decrease. And those are two situations in which we do have pretty darn close to conservation of mechanical energy, okay? And so they are very similar and do work in a very similar way. Equations for work done and all this stuff. Well, again, against gravity, it's just force times displacement. So how much force do you apply to displace the object vertically upwards? But in an electric field, it's a little bit different, right? I need to figure out work. It's done against the electric field. So it's done against where it would usually want to go. And you'd have to analyze that based on whether you have a positive or a negative charge. Okay, so work is still equal to force times displacement. Nothing can change that, but we can change around the equation a little bit, because electric force is equal to your charge times your electric field. We get that from an equation on your data sheet that says electric field is equal to electric force over charge. So that's just rearranged. And so then we can go ahead and take that and put it in for that force, and we get this equation, that work is actually equal to the charge times the electric field times its displacement, okay? And so for both of them, if you do work, then you'll have that gain in potential energy. So the potential energy is equal to, or the change in potential energy is equal to the work done, okay? But also we can still kind of measure change in potential energy using change in kinetic energy sometimes, because we know that as something loses its potential, it's gaining kinetic. Both these situations are situations in which mechanical energy is conserved. Obviously, with the gravitational, the dropping of the ball, that's only if it's not dropped too far above, right? If you drop the ball from the top of a skyscraper, absolutely air resistance is going to come into play, and we no longer have mechanical energy conservation. But the good news is, with electric potential energy, we're dealing with much smaller particles, and therefore we have very, very, very little energy ever being lost to heat. So we do have a nice conservation of mechanical energy, and therefore we can count on the fact that the change in potential energy will also equal and always equal to the change in kinetic, which is really nice. So sometimes we have the information to find change in kinetic energy, and that's going to help us find the change in potential, which is, of course, the work done on the system. Okay? Fun stuff. Let's talk a little bit about those parallel plates I drew. So this is how we get a nice uniform electric field. We really like putting things in between parallel plates, because when we're just talking about two charges, well, sometimes there can be other things around. But when I have two parallel plates here, we have a nice uniform electric field. So remember, electric fields always go from your positive charges to your negative charges. So the electric field lines in here will always be going towards your negative charge. It'll be going away from the positive charge and towards the negative charge. That doesn't mean everything's going to be moving to the right, because if I put a negative charge in that electric field, it's definitely going to be moving towards the left to the positive charge. So note that an electron is actually going to move against the gravitational field, but a proton would move with the gravitational field. Okay? So remember, those directions are arbitrary. It's just something we decided happened. And so since we have two types of charges, it won't always move with the gravitational field. With the electric field, unlike gravitational fields, which we always move with the gravitational field, which is towards the Earth, and we always fall towards Earth, or things fall towards Earth. But not so in this situation, because if I have an electron here, it's moving against the gravitational field, right? But if I have a proton in here, it's going to move with the the electric field. Wow, I'm really on gravitational fields here. So just keep that in mind. So just because the field lines are always going towards the negative plate, that doesn't mean everything's moving towards the negative plate. You still need to keep in mind what's happening with positive and negative charges and have that in context. Okay? So let's talk a little bit more about that strength between parallel plates, okay? I showed you a few of these equations already, but again, let's just take another closer look at them, because we know, of course, we need to do work to give something electric potential energy. We know that work is equal to the change in energy, which is also equal to force times displacement. And we saw that force is equal to QE because, of course, we did have this equation on your data sheet where electric field is equal to electric force divided by Q. And that's, of course, would be the force that a test object experiences. So we can go ahead and put this in for force. Okay. And so we get a new equation for the change in energy, and that's Q times electric field times E. So, oh my goodness, we are now at the situation where we are using energy and electric field in the same thing. So remember, electric field will always have either the absolute value brackets around it, okay? Or we'll have a vector on top. So anytime you see that, or the E with a vector on top, we're talking about electric field. E without either of those is energy, okay? So I know it's going to start getting real messy here. So make sure you are paying very, very close attention to those darn E's. Okay, we can break this down a little bit more because we know, first I'm going to rearrange. I'm going to divide both these sides by Q. Reason being is because I know change in energy over Q is equal to something that I just taught you at the beginning of this lesson. And that voltage is equal to the change in energy over Q. So here we go. We found another equation for voltage, and that is that it's equal to the electric field times the displacement of the thing that we're displacing to do the work on, okay? And usually we're displacing it all the way across the parallel plates. So that D there is actually the distance between the parallel plates. So this is specifically used for voltage in between a uniform electric field in or between parallel plates. This equation shows up like this on your data sheet, okay? It is under electricity and magnetism. It's the bottom equation on the left-hand column, and it is right there. So there we go. Electric field is equal to voltage times displacement, and that's the distance between the plates. But you can, of course, rearrange that to get that voltage is equal to electric field times the distance between the parallel plates. Okay? But that is specifically for when we're looking at the uniform electric field between two parallel plates, and then you're putting a test object in there, and it's moving across the plates. Okay. Whew. So hopefully that was enough information about voltage for you, because now we're going to do a few examples. Okay. So I want to know, how much energy is an object whose charge is 2 microcoulombs gain if it's accelerated through a potential difference of 200 volts. Give the answer in electron volts. Okay, so I want to know how much energy does it gain? I have charge, I have voltage. So if we look at all the equations I just gave you, which again are under electricity and magnetism on your data sheet, well, I have volts, I have charge, I want change in energy. So there's actually, surprise, surprise, just one equation that we could use. Well, I think we have to do some rearranging, but we don't even have to do any substitution, which is pretty nice. Doesn't happen a lot. So really, if I want change in energy, I just want voltage times Q. There we go. Well, that's nice. How often does that happen in Physics 30? Almost never, so enjoy it while it happens. Voltage is 200.0 volts, and your charge is 2 microcoulombs. Now, remember, micro is 10 to the negative 6 coulombs. Again, that's under the prefixes. And so you get, with that, 4.0 times 10 to the negative 4 joules, okay? Anytime you have volts and coulombs, that's when you're going to get joules. But it says give your answer in electron volts. So I'm going to need to change that to electron volts. Well, I know that for every 1 electron volt, I have 1.6 times 10 to the negative 19 joules. So if I have 4.0 times 10 to the negative 4 joules, I'm going to set up my lovely little equation here, or what am I trying to, conversion fraction, where I want joules to cancel out and I want EVs. So I put joules on the bottom of the fraction and EV on the top so the joules cancel out. And then I put in the relationship I know, and that is for 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Okay? And then there we go, joules cancels out. If we like doing that step, which I always do because it's very satisfying. Like, oh, joules are gone and electron volts are left. And I should get 2.5 times 10 to the 15 electron volts. Okay? And so that would be the equivalent of, what am I trying to say? That would be the equivalent of 2.5 times 10 to the 15 electrons passing through 1 volt. Okay? And that's pretty much, or 1 electron passing through 2.5 times 10 to the 15 volts. And that's what an electron volt is. Okay? Let's do another example. We have a proton being placed in an electric field between 2 parallel plates. The plates are 6 centimeters apart, so we have the distance between the plates, and have a potential difference of them between them of 75 volts. Okay. A, how much work is done against the electric field when the proton is moved 3 centimeters parallel to the plates? Let's picture that again. What do parallel plates look like? Well, there's one, right? Say this is our positive one. So let's say this is our negative one. Let's say I'm placing the proton near to the positive plate. So here's my proton. But I'm going to move this 3 centimeters parallel to the plates, meaning either up or down, because the plates go up and down. Is that doing any work? No, the electric field is going this way. I only do work if I move it against the electric field, or parallel to the electric field. I'm moving it perpendicular to the electric field, parallel to the plates. There is no work being done. 0 joules, okay? The charge must be moved parallel to the field. Which is also perpendicular to the plates. So, trick question. Let's move on. Part B, how much work would be done against the electric field if the proton were moved 3 centimeters perpendicularly to the plates? Okay, now we're talking, because now we're actually talking about a situation in which our electric field is horizontal and we're moving it horizontally because I'm moving it perpendicularly to the plate. So say I move this, actually let's move our proton, say it was in the middle. Okay, and say I am moving it 3 centimeters against here. I'm moving it there. Say that's 3 centimeters. Okay, so I want to know how much work is done when you do that. Okay, and so we're going to have to take a look at what our equation for work is. Let's do that. I need to move on to the next slide here. Okay, so let's figure out what is our equation for work. Well, that is force times displacement. We don't have the force being, we don't have the force, we don't have the force that's exerted. We don't actually have like what it is. We can definitely find it. Also keep in mind this d is the distance that the charge moves. Okay, so that would be the 3 centimeters. So what equation do we have for force? Remember, it's Q times E. E being our electric field in this one, so I'll put a vector over it so we know it's electric field and not energy, okay? Because we know that electric field is equal to the force divided by Q, so we just rearrange that. Okay, furthermore, I also don't have electric field, so I'm still stuck here. I want the work. And again, I'm trying to express work in terms of just a bunch of stuff I know. So I also don't know what the electric field is. So I need to come up with an equation for electric field in terms of stuff I know. So if I look at this equation, electric field is equal to change in voltage over the distance between the plates. Oh, I think I have that. Because I do have how many volts are between the plates when they're 6 meters apart. So there we go. But the trick here is now we have 2 different distances. So I can absolutely substitute in voltage over distance in there, but we need to know that that distance is the distance between the plates. So that is what really makes this a bit of a tricky situation is we have 2 different distances, okay? So we do have to keep in mind and be careful about that. But now when we look at this equation, we have the charge because, of course, it's a proton. So we know the charge of a proton. We have the voltage. We have the distance between the plates. And we have the distance that we are moving the proton against an electric field, which is, of course, very important when we're talking about work, okay? So I do actually have all of these values now and can actually find work. And that's really all I'm doing is I'm just like saying, okay, I know work is equal to this, but I don't have this. So what else can we do? And then that's that, and then that's that. And you just kind of keep going until you've figured out what the heck's going on. So remember, we had centimeters on the previous page. We had 6 centimeters, but we want meters. So that's, of course, 0.06 meters. And then we multiply this by, it was 3 centimeters that was being moved, which is 0.03 meters. Okay? And we get that it's doing 6.0 times 10 to the negative 18 joules of work. So really not a lot of work goes into having to do that. So there you go. Any of us could do that. No problem. No problem whatsoever. Okay, let's do one more example. So we have an alpha particle. Alpha particle, remember, has a positive 2 charge. It's starting from rest. It's accelerated towards the negative plate, which makes complete sense because we know alpha particle is positive is going to go towards the negative plate of a parallel plate apparatus. The potential difference across the plates is 2,000 volts. Determine the speed if this particle starts next to the positive plate at a point midway between the plates. Okay? So how do we decipher between the two? Well, we can decipher in 2 ways. We can decipher by the distance between the plates. Problem is we don't have that, right? So the other way we can decipher the difference between starting next to the positive plate and starting at the point midway, well, remember the voltage depends on the change in energy. So if it's halfway between the plates, well, that's going to be half the amount of voltage, okay? So this guy is when it's experiencing the full potential difference or the full voltage. And then if it's at a point midway, that's when it's experiencing half of the potential difference. And that's totally how voltage works, right? Halfway between, there's half as many volts that it's going to experience as it moves towards the negative plate. Okay, so keep in mind that is how volts works. Okay, so if I know that it's starting next to the positive plate and I want to know how much speed it's gaining, well, really what I'm going to do is I'm going to look at kinetic energy. I want to know how much speed it's gaining. So why not look at kinetic energy? That actually makes the most sense to me. Okay. And so actually, before we do this, I'm going to draw a diagram because why not? So we have our positive plate. We have our negative plate over here. And we have our proton either starting here, or no, alpha particle, oopsie. We have our alpha particle either starting here, okay? And that's gonna go across the full 2000 volts, okay? Or we have our alpha particle starting right in the middle, and it's gonna go halfway across, and that's actually only experiencing 1000 volts. So we know at this point, we have our maximum potential energy. Okay, and at this point we have maximum kinetic energy. So guess what we have halfway through? We have halvesies, okay? But again, if we just change how much voltage that it's experiencing, we can still actually find a new potential energy for halfway in between. Okay, so we are going to use conservation of energy here. Anytime you really want to find velocity, we're probably going to be going into kinetic energy and looking at conservation of energy. So let's do this. So for part A, with starting next to the positive plate, so experiencing the full 2000 volts. Well, again, I know the sum of energy at any one point is equal to the sum of energy at any other point. But I'm looking at a point when I have full potential energy converting itself into full kinetic energy. So when we're talking about potential energy with electric forces, though, that is going to be the charge times the voltage, right? Because voltage is equal to change in energy over Q. And so now, of course, then change in energy is QV. And kinetic energy is still at same old 1/2 mv squared. Okay, and then of course it doesn't have any velocity to begin with. We're assuming it starts from rest. So that's just its final velocity, which is what we're looking for. So final velocity here. Okay, just really make sure that this is a capital V. Another thing you can do to make sure that you know that's voltage and this one is velocity is put like a strike through it. So I have seen people do that. So solving this for the final velocity, we have 2 times Q times the voltage divided by the mass of the proton, because that's the thing that's moving, and you square root it. And let's find that final velocity. I think I said proton. I meant to say alpha particle. And you do have the mass of the alpha particle on your data sheet as well. And we get our final velocity as 4.387. We do need 4 significant digits if you look at this. Got 4 there, and that's all that was given to us. So we need 4 significant digits, so 4.387 times 10 to the 5 meters per second. And there we go. Okay, so that's the final velocity if it started right next to the positive plate. Again, now I want if it starts halfway in between. Now, the thing is it's starting halfway in between. So we're not assuming that it has any velocity there. So we're still assuming the velocity there is 0. Okay, so what makes it different is the fact that it's actually experiencing half as much voltage then. Okay, so we're pretty much going to do the same thing where we have the sum of energies initially should equal the sum of energies finally. And of course, initially it just has all potential and finally it just has all kinetic, but now it only has half as much potential energy. Okay, which does mean it's going to have half as much kinetic energy, but that does not mean it's going to have half as much velocity, because kinetic energy and velocity are not directly proportional. So this is still going to be QV is equal to 1/2 mv squared. Okay. But now, of course, our voltage is going to be 1,000 instead of 2,000. Otherwise, this question is going to look very, very similar. Okay. And we get a final velocity here of 3.102 times 10 to the 5 meters per second. So that definitely slowed it down, but definitely not halfway. It's not half as much speed. So that just goes to show you, never just assume that's half, because of course we square the velocity. And that's that. That's how to deal with potential and potential energy. So remember, usually we're talking about voltage when I say potential difference, okay? And potential energy is just potential energy.